Hey everyone, my name is Devin Hoskins. This is my ECE 591 literature review. My topic for this presentation will be VIT-ADAPTER implementation. So for today's presentation, the agenda is as follows. I'll start with a brief introduction, and then I will go into the key concepts and the implementation in code for the VIT adapter. And then I'll mention some results from this model. In this presentation, I will be reviewing the paper written by Shen et al. Titled Vision Transformer Adapter for Dense Predictions. If this title sounds familiar, it's because Jason Holliday also reviewed the state-of-the-art paper for semantic segmentation. In his literature review, he described the key concepts of the Vision Transformer Adapter. In my presentation, I will be going into detail on the implementation and code for this VIT adapter model. Before getting into the code, I would like to recap the key concepts of the adapter modules that work together with the plain vision transformer in creating a state-of-the-art semantic segmentation model. The goal of the Vision Transformer adapter is to utilize the multimodal pre-training ability of the plain VIT without modifying its architecture the way a vision-specific transformer does. The plain VITs can be trained using video, image, or text, making them easier to train and also encourage semantic-rich representations. After training, the plain VIT can be fine-tuned using the adapter as shown in Figure B. The adapter is not pre-trained and provides the plain VIT with the image-related prior knowledge that it lacks. Here we see the block diagram overview of the VIT adapter. First, we'll briefly look at the plain VIT. This is the vision transformer that many of you are familiar with. It first creates patches of the input image, flattens and projects these patches, and then embeds them with positional embeddings to input to a transformer encoder. These values no longer contain pixel information and are commonly called tokens, which are matched with positional embeddings. The tokens are input to the transformer encoder, which uses a multi-head attention and a multi-layer perceptron layer, each with layer normalization proceeding. Both layers also have residual connections where inputs are summed with their respective outputs. The output of the transformer encoder is then classified by an MLP head. Now I will describe the adapter modules and their functions. The highlighted blocks consist of the spatial prior module and the feature interactions, specifically the spatial feature injector and the multi-scale feature extractor. As you can see, there are n blocks of transformer encoder layers. For each block, there's a feature interaction consisting of the spatial feature injector and the multi-scale feature extractor. Each block contains L over N transformer encoder layers, where L is the total number of transformer layers. At a high level, the spatial prior module creates spatially represented tokens to input to the injector. Cross-attention is performed in the injector module. The spatial prior module's tokens are the key and value, and the patch embedding tokens from the plain VIT are the query. The output of the spatial feature injector is injected into the plain VIT as well as the multi-scale feature extractor. The extractor takes the spatial prior module's output as the query and takes the VIT tokens as the key and value and performs cross-attention once again. This is then input to a feed-forward network to extract multi-layer features from the VIT. The VIT adapter is implemented by creating PyTorch modules. Modules are created for the spatial prior module, the spatial feature injector, and the multi-scale feature extractor. There are also modules created for a convolution feed-forward network, its depthwise convolution, and the interaction block, which combines the injector and extractor. Included in the same .py file are functions for get reference points and deform inputs that are utilized in multi-scale deformable attention, which I'll explain in more detail later. The VIT-ADAPTER.py file then uses the modules from the adapter file to implement the SPM, injector, and extractor. The code on this slide are from the VIT-ADAPTER file. First, you see that the plane vision transformer and adapter modules are imported. A module is then created for the VIT-ADAPTER, where adapter modules are then initialized for utilization on the right. Next, I will talk in more detail about the adapter modules themselves and the code used to implement them. Now I will describe the spatial prior module in more detail. The spatial prior module is designed to model the local spatial contexts of images. This works in parallel with the patch embedding that is used in the VITs. This way it does not interfere with the original architecture of the plane VIT. A standard convolutional stem borrowed from ResNet consists of 3 convolutions and a max pooling layer. Then a stack of stride 2 3x3 convolutions are used to double the number of channels and reduce the size of the feature maps. Finally, several 1x1 convolutions are used to project feature maps to D dimensions. The result is a feature pyramid which contains D dimension feature maps with resolutions of 1/8, 1/16, and 1/32 of the original image. These feature maps are then flattened and concatenated into feature tokens as the input for feature interactions. Here is the class created to implement the spatial prior module. First, we have the convolutional stem that was borrowed from ResNet. Here we can see the 3 convolutions and the max pooling layer. You'll notice there are also normalization and activation layers following each of these convolutional layers. In PyTorch, the first 2 arguments of convolution 2D are input channels and output channels. So the images are input with 3 channels and then changed using convolution to be set to in planes, which you'll notice is initialized to 64. The first convolution has a stride size of 2, effectively decreasing the resolution by half. Then the resolution is halved again from the max pooling layer while maintaining 64 channels. Next, we have the stack of stride 2 3x3 convolutions. Convolution 2 increases channels to 128, while convolutions 3 and 4 increase the channels to 256. Each of these convolutions half the dimension size. This is where the 3 resolution sizes of 1/8, 1/16, and 1/32 will come from. Finally, some 1x1 convolutions are applied to project the feature maps to D dimensions. Their channels are set to embed_dim, which is initialized to 384. Next, we will see how all of these are applied to create our feature pyramid. Now the functions created on the last slide are implemented. Say the input x is 224 by 224 by 3. The first set of computations is the stem module, which creates a feature of 1/4 the resolution. Tensor C1 will have a shape of 56 by 56 by 64 channels. Then 3 more features are created, C2, C3, and C4. These features have dimensions of 28 by 28 by 128, 14 by 14 by 256, and 7 by 7 by 256, respectively. The next set of computations are the 1 by 1 convolution layers to project the features to each have 384 channels. These features each keep their respective resolutions. The feature maps are then reshaped using the view function and transposed for further interactions. In the VIT-ADAPTER module, the features are then flattened and concatenated. The second adapter module is called the Spatial Feature Injector. As the name implies, it is used to inject spatial priors into the plain VIT encoder. It takes the tokens from the spatial prior module and performs cross-attention with the tokens created in the plain VIT process described earlier. For the cross-attention, the VIT tokens are the query, and the SPM tokens are the key and value. As shown in the equation, normalization is applied to both the VIT image tokens with the positional embeddings and to the spatial prior module's feature tokens. Then cross-attention is applied. Gamma is a learnable vector, which is used to balance the attention layer's output and the input feature. Gamma is initialized to 0 in order to ensure that the feature distribution of the input features will not be modified drastically. This is the Spatial Feature Injector module implemented in code. Here we see the layer normalization initialized in preparation for the cross-attention. Then they initialize the attention layer and the learnable vector gamma. The attention used is called multi-scale deformable attention, which attempts to avoid high computation costs, overfitting, and the dropping of relevant or important keys and values. The highlighted code shows that the injector module returns the modified VIT block input as described by the equation. In a paper written by Shaw et al. Titled Vision Transformer with Deformable Attention, they proposed deformable attention to mitigate the issues of high computation costs in creating feature maps with influence from relevant parts beyond regions of interest. For each attention module, reference points are first generated as uniform grids, which are the same across the input data. Then an offset network takes the query features as an input and generates the corresponding offsets for all the reference points. This shifts the keys and values towards important regions. This image represents some different applications of attention for transformer models. Figure A is the plain VIT, which learns full attention for all queries. This can be a large use of computational power. The swing transformer in figure B attempts to avoid this excessive computation when using attention, but has likely dropped some relevant features in the process. Figure C shows the implementation of the deformable convolution network, which learns different deformed points for each query. Finally, figure D shows the deformable attention transformer, which learns shared deformed points for all queries and is very focused on the relevant features of the input image. The attention used for both spatial feature injector and the multi-scale feature extractor is multi-scale deformable attention. Here we can see in code how the reference points and the deformed inputs are created. The reference points are defined uniformly across inputs for each of the resolutions in the feature pyramid. The deformed inputs are also created for each of the different feature map resolutions. Feature interactions. After the spatial features from the spatial feature injector go through a block of transformer encoder layers, the output of that block is extracted. Multi-scale cross-attention is performed again. This time, the query is the spatial feature tokens, and the key and value is the output of the transformer encoder block. The generated spatial feature is fed into a feed-forward network as shown. Then another block of encoder layers and feature interactions is computed. Equation 1 shows that both the spatial priors and the output of the VIT encoder layers are normalized and attention is applied. This is then summed with the previous spatial features and then fed into the feed-forward network depicted in equation 2. The result is the spatial priors that will be fed into the following feature interaction block. The multi-scale feature extractor uses the same multi-scale deformable attention as previously described. It then feeds the result into that feed-forward network. The convolution feed-forward network consists of a depth-wise convolution, which is a type of convolution that has less parameters and therefore takes less computational power and is less prone to overfitting. First, a linear transformation is performed, then the depth-wise convolution. The JLU activation layer is applied, and then another linear transformation and dropout. These features are the input for the next feature interaction. In depth-wise convolution, a single convolutional filter is applied for each input channel. Remember, in regular convolution, the filter is as deep as the input channel. So if the input has 3 channels, the filter also has 3 channels. In depth-wise convolution, each channel is kept separate. The input and the filter are split into channels, and each input is convolved with its respective filter. Then the convolved outputs are stacked together. This results in less parameters than regular convolution. For semantic segmentation, the VIT adapter is evaluated on the ADE 20K dataset in MM segmentation codebase. Both semantic feature pyramid network, FPM, and UpperNet are used as the basic frameworks using 80K and 160K iterations respectively. The results are reported in terms of single scale and multi-scale intersection over union, or IOU. The table shows the different VIT adapter models, tiny, small, big, and large, against other state-of-the-art models and the plain VIT models. The pre-training was done on both ImageNet 1K and ImageNet 22K, as well as a multimodal dataset. On ImageNet 1K pre-training, the VIT adapter small outperformed models such as the Swin transformer and the plain VIT by achieving 47.1 multi-scale IOU with UpperNet. The VIT adapter big outperforms the VIT big by 2.6 and tied performance with the Swin transformer big. Using ImageNet 22, the VIT adapter big and large outperform the Swin transformers of the same class by 0.8 and 0.9 respectively. While the multimodal trained VIT adapter achieves 55.4 multi-scale IOU, topping Swin large by almost 2. This image shows the object detection performance on the COCO VAL 2017 dataset across the 4 VIT adapter models and other strong models. Object detection performance was measured in average precision. The plot shows that the VIT adapter outperforms the other models in all class sizes. It also includes the VIT adapter big using multimodal pre-training, where you can see that again, the ability to utilize multimodal pre-training improves model performance. The multimodal pre-training is one of the reasons why the authors explored keeping the plain VIT architecture as opposed to the vision-specific transformers, and chose to fine-tune it using the adapter. Thank you for listening to my presentation, and here are my references.